All right, welcome everyone to another Quantum Matter seminar. Today it's my pleasure to give you Abby Timel. Abby, most of you don't know, but was an undergrad at Northeastern for a year and a half before she moved to UPenn. And there she worked with Jean Mele and published a few papers, and then moved to MIT, where is now working with Xiaogang Wen. And she's going to share with us her latest results. Thank you, Abby, for crossing the river to do this.
Thank you. Yeah, so I'm going to be talking about a theory we have for chiral superconductivity. And this is a theory that results purely from repulsive interactions. So it's going to be beyond the usual BCS framework, where we have an attractive interaction inducing pairing and an instability of the Fermi surface. And for most of the talk, I'll really be focusing in an interaction-dominated regime. Okay. So I'm going to start by talking a bit about quantum Hall states, because these are going to be a good platform for exploring interaction-dominated physics. And I'm going to lay out a condition for how we can generalize these to situations beyond Landau levels. And this theory will be kind of a rough argument, so we'll need some numerics just to show that this is going to be energetically favorable. And finally, I'll show that this condition for realizing these states outside of Landau levels, is also a condition for superfluidity. And that can also be argued using Chern-Simons theory. So I'll lay out some of that as well. So I want to start by thinking a bit about states that favor strong repulsive interactions. So the most obvious one is just a Wigner crystal, where the electrons are localized far apart from each other. But we can also have a correlated liquid state where the electrons are still correlated to be far apart from each other, but now the correlations are such that the state is uniform density. And we can think of this kind of as a melted Wigner crystal. And there's some experimental motivation for thinking about these states. This is data from Longju's group at MIT, from tetralayer graphene, and they found these superconducting states that appear very close to Wigner crystal states. And two of the superconductors are quite conventional. That's this SC3 superconductor and SC4. They're fairly smooth in contrast to the other two, which have these strong fluctuations. And when you put on a magnetic field, they're destroyed around 0.1 Tesla, which is consistent with other graphene experiments. But in tetralayer specifically, they also see these other two superconducting regions. And these are very unusual. You can see from this data that they have these strong fluctuations between scans in the X direction here. And this is kind of reminiscent of a valley symmetry breaking effect, because this data was taken at zero magnetic field. And in a valley polarized state, the state can switch between different polarizations between scans. And so this right away tells us that there's some kind of chiral effect going on, some kind of orbital magnetization. And they also survive to quite high magnetic field, which is unusual again. So now I'm going to talk a bit about quantum Hall states, which are going to be the basis for the class of wave functions we're going to consider explaining these interesting correlated states that appear near Wigner crystal. So to start, just to remind you, when we have a magnetic field, the single particle states form Landau levels, and in symmetric gauge, we can write the single particle wave functions in this form, where we define a complex coordinate z, and we're allowed to have any power of z here. So that generalizes to any holomorphic function times this exponential factor. And the decay length of the exponential factor is set by the magnetic field. So it comes into this magnetic length here. And when the lowest Landau level is fully filled, it's easy to write down the ground state. It's just an anti-symmetrized product of these single particle orbitals, which we can rearrange into this Zi minus Zj form. So when we have a partially filled Landau level, the situation is more complicated because there are many states in the Landau level and many ways to fill them. So Laughlin wrote down this wave function, which is designed to favor repulsive interactions. And it does that by putting an mth order 0 between every pair of particles. This wave function has some nice features. It turns out to be uniform density at low m, and when you go to high enough m, it transitions to a Wigner crystal. So this is right away the kind of state we are interested in. It's near a Wigner crystal, but at high enough density, so low enough m, it transitions to a correlated liquid. The state is also incompressible, and the easiest way to see that is by noticing that the only way to change the density is by changing this exponent m, because the exponential factor is rigidly fixed by the magnetic length. And m has to be integer to make the wave function single valued, specifically odd integer if it's fermionic. So the only way to change the density is by bumping m up an integer value. And that's kind of a discrete change. So the excitation will be get. We can generalize this further by allowing multiple species of electron. So here we've denoted different powers of Zi minus Zj by whether they're between the same species or between different species. And here the species can be any sort of quantum number labeling an electron. So it could be like the spin or the valley in graphene. And we just require that Kii, so the diagonal components, are odd if it's a fermionic state. And we can also include negative exponent or negative Kij, which we just take to mean the opposite winding. So we include a Zi star, where star is the complex conjugate minus Zj star, and raise that to the absolute value of K. Okay, are there any questions so far?
If you're in the online audience, please feel free to mute yourself if you have questions.
Okay. So this state, or these states, are along the lines of what we're interested in for this situation, they clearly favor repulsive interactions. They're near a Wigner crystal, and we can start to make them quite general by including multiple species and anti-holomorphic as well as holomorphic components. So there's one question, which is whether we can realize this kind of state in zero magnetic field, because that's where the experiments were taken. And the problem with this is that once you start to include phase winding, which is present in the Zi minus Zj components, this in general will push the states out to very high angular momentum. And when we're in a flat band, like a Landau level, that's perfectly fine because the band is flat across the entire Brillouin zone. And so pushing the momenta out doesn't cost any kinetic energy. But if we were to try to realize this in a dispersive band, which graphene is even for tetralayer, which where the dispersion is closer to quartic. So we need a way to kind of mitigate this angular momentum explosion. And it turns out there's a way to do that. So we can kind of count up the net winding in the system.
Sorry.
Yeah.
When you talk about different species, which you have in mind is different speed.
Yeah, so spin is one. There could be valley. So those are the two things we'll consider in the graphene case, spin and valley. There could also be other ways of having multiple species. Yeah, like if there's some magnetic flux through the system, sometimes the band structure is copied multiple times over the Brillouin zone, so you get different minima, and those minima are labeled by crystal momentum that also gives you a different quantum number. So that's another case we explore in our paper. Okay, so we want to make the momenta stay close to the band bottom. And there's a way to do this. We can make a rough argument by counting up the net winding in the system. And to do that, we sort of notice that each particle in the R species sees a winding KII from every other particle in the I species. So there are n-1 of those. And it also sees Kij winding from each particle in the njth species. And so you can write down the total winding for the system. And you can see that this becomes linear in particle number rather than quadratic if K has a 0 eigenvalue. And if we fix the numbers of particles in each species to match the 0 eigenvector of that matrix. And in that case, the momentum is linear in particle number, so we can imagine orbital weight filling up the bottom of the band, similar to how it would for a Fermi liquid. So this ground state is still very correlated, but we expect the weight to be kind of as close to the band bottom as it would be for a Fermi liquid. So with this in mind, we can start to write down a trial wave function for realizing these states outside of a magnetic field. And the first thing we'll do is allow both holomorphic and anti-holomorphic components because we're no longer restricting to the lowest Landau level, so we can have powers of Z star. And so here I've just copied the multi-species zeros and included powers K plus for the holomorphic components and power is k minus for the anti-holomorphic. And then we also need to figure out what to do with this magnetic length in the exponent. So since the magnetic length was set by the external magnetic field, it's less clear what that will be in the absence of a magnetic field. So we just make it a variational parameter for each species. So we allow an L sub I that gets tuned independently for each species. A few things to notice about this wave function are that it has a Kij plus Kij minus order 0 between species I and J. So we'll call that K bar. And it also has winding numbers that are set by Kij plus minus Kij minus. And these are required to be integer to make the wave function single valued, as I mentioned before. And these are this is the matrix that we require to have a 0 eigenvalue in order to make the winding numbers cancel and give us momentum, linear, and particle number. So that will be a constraint on what the K plus and K minus can be. And we also need a condition on these L sub I, because if we tune them completely independently for multiple, for each species, then we could end up with a situation where one species is occupying a very small area and another species is occupying a very large area. And we want the droplet sizes to agree. So all the species occupy the same area. And the condition to do that is just this here, which depends on the K bar. Okay. Any questions about the Chiral wave function? Yeah. Yeah, so anti-holomorphic, or so you get Z stars when you go into higher Landau levels. We're not going to worry about that too much because this Chiral wave function is outside of Landau levels altogether. But yeah, if you could write this down in terms of the higher Landau levels, and it would probably be more complicated. But the motivation for this wave function is really outside of Landau levels. So we're taking the view that it's just something you can write down, which gives you an order of 0 between particles, so favorable to Coulomb interaction. And there's some winding, which can be given by either a holomorphic 0 or an anti-holomorphic 0, and we're not distinguishing between the two of those. And then we need an exponential factor so that the polynomial part decays at some distance. And this whole thing ends up being uniform density for low values of K. Yeah. So it was motivated by Landau levels, but it's being utilized for different reasons than Laughlin's original argument. So the argument for the angular momentum staying close to the band bottom was very rough, and we really need to do numerics in order to confirm that. And so this is also a good time to specialize to tetralayer graphene. So tetralayer graphene has a dispersion that favors the quartic term, so k to the fourth. It's purely k to the fourth in kind of an ideal limit, but once you start to include other realistic hopping terms, you get a k squared component. But you can tune the k squared contribution with a displacement field, which is an out-of-plane electric field. The experiments were done at densities around 10 to the 12th particles per centimeter squared. And in this dispersion, which I've plotted for a tight binding model that includes a lot of hopping terms. And this is for kind of a typical displacement field in the experiment, and for a typical density 10 to the 12th particles per centimeter, a Fermi liquid would just sit right in this flat region. So in the data, as the displacement field is tuned up, this region would get even wider. And if it's tuned down, then it would get more dispersive in this region. We also know that for graphene, we can have up to 4 flavors of electron. So 2 for spin, 2 for valley. And this will guide what kind of K matrices we come up with. And these are some of the K matrices we looked at. So we have examples for 2 species, 3 species, and 4 species. The requirements are just that it has a 0 eigenvalue. We also require that the eigenvector for that eigenvalue has positive values in all the components, which just means that the particles will be positive density, which we kind of need for it to make sense. Another thing is that we need all odd integers on the diagonal, which makes the wave function fermionic. Okay, so going back to the experiment for a minute, we know that the states kind of at densities above the superconductors are quarter Fermi liquids. And that means that the Fermi liquid is completely spin valley polarized. So electrons are only occupying one of these 4 species we're allowed to have. And those quarter Fermi liquids occur above like 10 to the 12th particles per centimeter. And we know that Wigner crystals start to appear below 0.5 times 10 to the 12th particles per centimeter. And this is just some data showing why we know the Fermi liquid is a quarter Fermi liquid, and it's because when you put on a magnetic field, you can detect these quantum oscillations, and the period of those matches what you expect for a quarter Fermi liquid. So this is Monte Carlo done for each of the K matrix states in the previous slide. And on the left here, we have the energies for quartic dispersion, so K to the 4th. And on the right, we have energies measured for quadratic dispersion. And these are all plotted as a difference between the K matrix state and a quarter Fermi liquid state. So when they start to appear below 0, that's when the K matrix state will be favored over the quarter Fermi liquid. And we know that Wigner crystals start to appear around 0.5 times 10 to the 12th particles per centimeter. So that's going to be like around here on this plot and way off to the right on this plot. So right away we can see that K matrix states are not really going to appear before Wigner crystals start to win for quartic for quadratic dispersion, but for quartic dispersion, there is a window where the K-matrix state starts to win over the Fermi liquid, but the Wigner crystal might not be appearing yet. And in particular, it's the K2A state and maybe the K4C state that enter in that regime. So these are kind of the ones we'll be interested in. Any questions? So now, oh, you do.
Sorry. So, what's that time?
So it's a Coulomb interaction, so 1/r, and the kinetic energy, it's k to the fourth for the left and k squared for the right. And there's a way to make the Green's function nice enough to compute very well with Monte Carlo, which is a long calculation in our appendix. So the output from the Monte Carlo was pretty much a Green's function and a 2-point correlation function that you can get the interaction energy from. Okay. So we would like to have a better idea of how many species might be entering into these superconducting states experimentally. And there are a few clues from the neighboring states. So we know that on the right of the superconducting state, it's a quarter Fermi liquid. And we can see from this plot of RxY that there's an anomalous Hall conductance in that region, which we expect because a single valley has net Berry curvature. There's also magnetic hysteresis measured at points both in the quarter Fermi liquid and kind of on the boundary between the Fermi liquid and the superconductor. So this is a good indication that the states around are breaking valley symmetry. So we know that quite well. We also know that if you take the temperature above Tc and measure the same things in the normal state above the superconductor, you also see non-zero Rxy and hysteresis in the in Rxy. And this is unusual for a superconductor, and it would be unusual if in the transition it went from being valley polarized to not valley polarized, but we can't really conclude that from this data alone. It could be making any sort of transition from one species to multiple species. And we can't measure directly Rxy, obviously, or any sort of like quantum oscillations because there's no Fermi surface in the superconductor. So a better piece of evidence that the superconductor continues to break valley symmetry is this plot as a function of Rxx as a function of magnetic field. And what we expect is that if the superconductor is not breaking valley symmetry, then once you put on a magnetic field, the quarter Fermi liquid, since it does break valley symmetry, will be lowered in energy from the Zeeman effect. But if the superconductor has weight in both valleys, then the superconductor would not be lowered in energy. And so we'd expect the quarter Fermi liquid to be favorable to lower densities as the magnetic field is turned up. And so we'd expect this boundary to kind of move to the left. But we see that it remains very flat. And so this is a pretty good indication that the superconductor continues to break valley symmetry. So we can expect either one or two species from the spin at this point, since the Zeeman effect from the spin is so tiny, it wouldn't necessarily show up here. Any questions? Yeah.
So this might be a dumb question. Could you explain what you mean by a value symmetry again?
Oh, valley symmetry? Yeah, so graphene has two valleys. So there's the K point and the K prime point. They're inequivalent points where the band has a minimum. And in graphene experiments, the electrons are often like spin valley polarized. So energetically, you might expect them to occupy both valleys, but there's some exchange effect that makes it favorable for them to all be in one valley. And that's a situation where since the valleys have opposite barrier curvature, now you have all of the orbital weight in one valley, and so there's orbital time reversal symmetry breaking. And that's a bigger effect from spin polarization, from a Zeeman effect standpoint, because the orbital time reversal symmetry breaking is going to couple more strongly to the magnetic field.
That's a great explanation.
Okay. So we know that there could be either one or two species involved in this superconducting state. And we have a theory for two species, but we don't really have a theory for one species yet, because a K-matrix that has only one component and needs to have a zero eigenvalue can only be one thing, and that's zero. So we can try to write down a state that has this property. K plus and K minus are forced to be equal, so that K is zero, and so we end up with this absolute value. And we can't have a wave function that's fermionic that has this absolute value, because it won't be antisymmetric under exchange of particles. So we need to have some way of antisymmetrizing it, and we can do that with this Pfaffian term. So this Pfaffian is going to remove a holomorphic zero between every pair of particles for some pairing, and then anti-symmetrize over all possible choices for those pairings. And that's a less drastic effect than having a zero between every single particle and every other particle. So we expect to still see the same features that we wanted from our single component K matrix. So this is our guess for what a single component correlated liquid state would look like in this framework. And it's a candidate if the transition between the quarter Fermi liquid and the superconductor turns out not to be first order, because if it's going from one species to two species, we expect that to be a first order transition, and it's unclear from the data whether it is. So here's Monte Carlo for the Pfaffian state. It's slightly less well developed, or the tools for computing this are slightly less well developed than the K matrix state. So these energies maybe should be taken less seriously. But we see that again for quadratic dispersion. the states only start to appear well within the Wigner crystal regime. But for quartic dispersion on the left here, we see them start to appear here, which is not too far into the Wigner crystal that we wouldn't expect them to never happen. So this is, again, an indication that quartic dispersion is quite important for seeing these states. And we now have kind of two candidates, the K2A state and Pfaffian states. Any questions about the Pfaffian? Yeah.
So on these plots, what's the quantity being computed for Monte Carlo?
So the Monte Carlo output is a Green's function and a two-particle correlation function. So you can compute the kinetic energy from the Green's function and the interaction energy from the pair correlation function. And so that's being so the energy for a quarter Fermi liquid is being subtracted from that. And so once that starts to dip below zero is when the K matrix state is favorable over a quarter Fermi liquid.
So the QFL energy is just the melt out.
Yeah, yeah. Mm-hmm. So I've explained a lot about these states which favor repulsive interactions and could show up at the boundary between Wigner crystals and quarter Fermi liquids. But they saw superconductors in the experiment. So we might be wondering, where's the superconductor? And it turns out that these states I described are actually compressible. And we can see that by noticing that in the quantum Hall states, the reason they were incompressible was because the length scale in the exponent was fixed by the magnetic field. But when we went to a zero magnetic field case, there was no longer any preferred length scale. And we had this condition for fixing the L sub I relative to each other, but we can still scale them all by a constant, and the wave function is still completely valid. So it turns out that we believe there's a single gapless mode, and that comes from scaling all of these L sub I together. And if there's a single gapless mode, that means the state is a superfluid because there are no channels for backscattering. And since we required all of the densities in this zero eigenvector that's determining the density ratios, we required all those densities to be positive. That means there's a net charge in this component. And so it's not only a superfluid, but a superconductor. It's slightly easier to see that it's a superconductor if we look at the Chern-Simons theory. And to see this, we have to note that the K matrix gives a phase winding seen by all particles of one species from all particles of another species. And so this is the same as attaching a flux to every particle of one species that's seen by another species. And the way to write that down in effective theory is with this Chern-Simons term that dynamically attaches flux according to this K matrix. And we know that a Chern-Simons term gaps excitations if it's non-zero. But we recall that our K matrices always had to have a zero eigenvector. So we can decouple this eigenvector by doing a transformation, there are ways to do this which keep all of the charges integer, which we would like. But in that form, we can really see that there's a single mode described by densities according to the zero eigenvector of K, where there's no gapping from the Chern-Simons term. And all other degrees of freedom do have this now determinate non-zero K matrix, which gaps them. And so now it's kind of easy to see that the constraint which gave us angular momentum close to the band bottom was also a condition for zero net flux through the particles in a certain density profile. And that's a quantum Hall state that can exist at zero magnetic field, since there's zero net flux. And that's also allowed to fluctuate independent of the magnetic field, which is why we get to have a gapless mode. Any questions about this? Okay, so a few things about the chiral superconductivity. We can figure out the charge condensation by looking at our zero eigenvectors and multiplying through by some constant to make them all integer, and then adding up those integers. So that's kind of the smallest collection of charges you can have in that component. And if we do that for all of the K matrices we found before, we find a bunch that are charge 2e condensation, but we also find charge 4e condensation and charge 6e condensation. So these are very exotic superconductors. They're very clearly beyond pairing. The two superconductors that seemed most likely to appear in the experiment both have charge 2e condensation. And if you look at the vortex structure, you can see that there's usually like order 1, or in both of these, there was order 1 winding between pairs of particles. And so that means there's orbital angular momentum 1 for each pair of particles, which means that they're likely in the same phase as a P plus IP superconductor, spin triplet for the K2A state and spinless for the Pfaffian state. And when I say they're in the same phase, they're quite far away from the BCS realization of the phase. So there's no explicit pairing between individual particles. It's kind of a correlation between species. Okay. So what we found is that these correlated liquid states, which we got to just by considering repulsive interactions and states near Wigner crystals, turn out to be good candidates for chiral superconductivity. We kind of get a superfluid mode by virtue of them being realizable outside a magnetic field. We also found that quartic dispersion helps a lot with the appearance of these states below the energy of a quarter Fermi liquid. And this kind of shows why these states are showing up in tetralayer graphene, and we haven't really seen them in other systems, because tetralayer graphene kind of takes advantage of the quartic dispersion. We found two states that seem more favorable than other states for the experimentally observed parameters. And those were the K2A state and the Pfaffian state. We can't say for sure which it would be, but if the transition turns out to be first order, it's likely to be the K2A state. And if it's not first order, then it's likely to be the Pfaffian state. And I'd like to thank my collaborators. So Luke did the Monte Carlo. Xiaogong is my advisor, and we had experimental input from Wangju.
Thank you, Abby.
Mhm.
Very nice talk, very nice work.
Yep.
Any questions from the other?
Yeah, so I was wondering, could you go back to, how you're explaining the, how you count essentially the lowest, the integers and I'm sorry, I'm trying to ask how you can, like, what signature you see for, whether it's 2E, 4E, or 6E pair.
Yeah. Let me go back to the K matrices. Yeah, so these F are the zero eigenvectors. And to find the charge condensation, we want to make all the fields integer, because we want to think about an integer number of electrons in each species for that channel. So for these three states here, we just can have 1, 1, and so 1 + 1 is 2, and so these are charged 2e condensation. Here we can make this to be 1, 2, 1, and so add those up and it's charge 4. Here is going to be 1, 3, 2, so that's charge 6 condensation. And then these are all 4 again. Yep.
A couple of questions. So let's start with the most trivial one. Can't you compare also the variation of energy you get from by using a plain vanilla PCS wave function? So what you get compared to your wave function?
Yeah, we could we could probably do that. I think the reason we're not thinking about BCS is because it requires attractive interactions. And we don't have any attractive interaction in the problem.
So the second one is, you know, when you numerically study the laughing wave function, for instance, and you know, one thing people do is to calculate overlaps with the in small systems like spheres, cylinders. So, and to do that, you know, the laughing wave function has a very simple parent Hamiltonian.
Mhm.
And would it be possible for you to write parent Hamiltonian for your wave functions and do indeed functions in small clusters?
So write down a Hamiltonian and find the exact eigenstates or the
So-
ground state.
Right,
And then-
this, you know, for the laughing wave function, there's a Hamiltonian.
Yeah.
Its ground state is the laughing wave,
Okay.
and it's very simple.
Okay.
And just obeying Hamiltonian with the just one superpotential if you want.
Hmm.
And I suspect might be possible to do the same for something here. That you can probably do EP in small clusters and calculate overlaps between subgraph states and variations.
Okay. So since it's a pseudo potential, we just need enough of an order of 0. Is that the idea?
So you just have so the laughing wave function is not an eigenstate of the full Coulomb Hamiltonian,
Mhm.
but just a truncated sort of
Hmm.
version of the Coulomb Hamiltonian.
Yeah.
And maybe it's the same here, so you can
Yeah.
dice the Hamiltonian to get an exact. So your wave function in small cluster and calculate the overlap, right? Exact. State.
Yeah.
So you have two Hamiltonians, two ground states, you calculate the overlaps.
Yeah. Yeah, I guess in this case, we'd probably need a way for time reversal symmetry breaking to come in. I'm not sure if that's because in the Laughlin case, that's from the magnetic field. So I'm not sure if what sort of parent Hamiltonian would include that anomalously.
In that wave function, the overlaps.
Mhm.
It's just a couple of copies of the foundation, one for each. Maybe. I don't know, thinking out loud.
Okay,
But
yeah, maybe.
any questions from the online audience? Feel free to unmute yourself and ask that. No? Okay, no, let's thank Abby one more time.